So the previous videos have led up to the derivation of the oil equation. The oil equation is almost the Navier-Stokes equation, but it lacks the viscosity term. So in order to put in the viscosity, the viscous stress tensor needs to be used. So the basic concept is that there's going to be a fluid blob, as is kind of pictured here. And this is of course the notorious W blob at time t. That's been here the whole time. And what happens is as it moves along in its journeys, there's basically fluid flowing around the blob, flowing past it. And what happens is as fluid moves along, it actually drags on the surface of the blob. So if the fluid is moving faster on one side than it is on the other, or the fluid is inside the blob is actually moving slower than the total fluid flow, there's going to be a force due to the attractions between the fluid molecules that tend to go ahead and make adjacent fluid all flow at the same velocity. And this is basically the viscous force. So zooming in on this, and go to the skin. So this is the skin layer, and I'm dividing the skin into these little cells. So if there's a higher velocity flow, say along the top, than there is along the bottom, there's going to be a force on these cells caused by the viscous fluid. I'll go back to the whiteboard. So this is going to be the derivation of the viscosity tensor. So this is viscosity. Tensor. And I'm going to go over what that actually is. So basically, the idea is that a force due to viscosity is going to be proportional to a difference in velocity of fluid flow, and then times the surface area. So basically, and the difference in velocity is basically the difference in velocity across the surface. So if I have this surface of fluid, and then I have a velocity here, u, and I have another velocity down here, there's going to be some sort of viscous force that's going to be caused by the fact that there's fluid in adjacent layers are moving at different velocities. So if I take one of these cells in the skin, as far as I drew this thing, so we have all these little balls that kind of circles that kind of represent these skin cells, and just look at what's going on in one of them. So if I take one of these things and then try to figure out what the forces are on it. So I have this cell, and then I have a velocity going across here, which is going to be, I'm going to call this V1, and I'm going to call this V-1. So this will also have another velocity here, which is assumed is the same as V-1. So this is also V-1. So this thing is both the inside, this would technically be the skin of the blob, so both the inside of the blob and the skin are presumably moving at about the same speed. And then it has this distance defined as delta. So the amount that the blob skin is going to be dragged, the naive assumption for force viscosity, the dots like that, but the naive force viscosity would basically be proportional to the degree to which the velocity outside is going faster than the degree to which the velocity is moving in the blob. So it's basically the difference between this velocity and how fast the skin is moving. So the faster the external velocity is going, the external fluid is going, the more force there is on the skin of the blob to make it accelerate to match the external velocity. So V1 minus V. And another way of looking at this in the differential form is this would also be equivalent to the delta, which is this distance times the change ux over change in y. So basically V1 of course goes like, the V goes, ux goes like, in this case these guys are essentially different ux values. So the u, which is the velocity in the x direction, this is essentially the ux at that location. So the ux in that direction versus the ux at this direction is proportional to the change in the ux across this distance. And that should be proportional to the force of viscosity in the naive sense, but that is not actually what viscosity is. And the reason it's not what viscosity actually is actually because of vorticity. Vorticity will change everything. So it looks like this should just generate force, but the reality is if the velocity is going in one direction on the top and there's a velocity inside the skin going in the other direction, these sails can actually just start spinning around. So it ends up kind of being like rolls on a conveyor belt. So when these sails the skin just spins around and around in circles, there's no actual net force. Because all it's the change in difference in velocity is doing is spinning the skin. So the actual velocity looks actually different. Viscosity actually looks different. So here's the real viscosity. The real viscosity, let's start with this thing, the cell again. It has some sort of velocity. I'm going to go back to using u, assume it's mostly in the x direction. And what this actually looks like is it could actually be broken down into two types of components. So there's this component, which basically has a spin on it, and this could be added to another component that looks like this. Let's say I basically group it down. And then this guy is a vortex. So this guy does not, it keeps jumping off. Not contribute. It does not contribute to the actual force viscosity. So the only thing that contributes is actually that guy. So to make this even clearer, I'm going to redraw this in simple form. I'm going to redraw this skin cell actually as a square. Here was this. I have the delta. It's going to be the half width. And this is going to equal, I'll use some colors here. Trying to get this thing to work. Okay. Okay. That's going to equal basically the vortex part. And then it's added to another flow. And this is basically going to be the shear part. So basically this arrow cancels this arrow, that arrow cancels that arrow, that arrow cancels that arrow, but these two arrows add. So this is basically circling around in a circle, does not contribute to force, and only this flow actually contributes to force. So the way to write this out is this way. So you basically have du x dy, which would be the expected term, times so that would be basically the expected difference in velocity between the top and the bottom. Oh, I'm actually going to erase that. So this basically corresponds, this guy basically corresponds to the entire block, the expected dux dy, so there's a difference in velocity from the top to bottom of this skin cell. This is what would be expected. But then there's these two other terms. And this term base equals 1/2 this is dux dy minus dy dx plus again plus dy dx. So this is basically just very simple algebra, as well as this term cancels that term and these two sum, and then the 2 comes up on top. So this is just by definition. However, it turns out this term corresponds to that type of flow, which is the vorticity flow, and this term, the blue term, actually corresponds to the shear flow. And it is only the shear flow that actually contributes to the vorticity. And for those who watched the optional section, this was derived as omega. Omega, which goes like rotation. Cell. So this goes like the rotation, which is the vorticity. Whereas this is the shear. Erase that. Okay, so the important part to know is that only that contributes to force viscosity. So dux dy plus the duy contributes to the force of viscosity. In this case, in the x direction is as it's defined. So, going back to the sequence. So basically the one part does not contribute at all, but there is a force that's caused by the upper whale moving faster than the lower whale, and that causes a force on all these little skin cells that actually goes ahead and causes this tangential drag on the skin. So for the tangential drag, that is kind of the sideways drag, as the whale on top of the skin moves faster than the whale below it. That has to have that extra term in order to go ahead and correct for what otherwise would go ahead and otherwise the spin would actually get incorrectly counted as part of the force. Okay, so that's it. So much for the side force. So there's also another type of viscosity, and this is basically the forward viscosity. Okay, so forward force of viscosity. This was, in a sense, the shear viscosity. So this comes from whales sliding over each other. The fluid viscosity basically comes from the fluid, in a sense, attempting to separate from other fluid. So we have this fluid blob, and there's a higher velocity going in that direction, and then a lower velocity in this direction. There's actually going to be a viscous force. And this, in some sense, could be described as kind of a separation viscosity. And it turns out this is much simpler, and the formula is fairly obvious. So the force viscosity here is simply proportional to the difference in the velocity. So d, and let's say dux, dx. So it basically just goes like, if the velocity is, the ux is slower here and then faster here, the more of a difference in velocity there is across the skin, the stronger this force viscosity. That's basically the separation. So bob and go back out. So this is the front of the thing, and so there's a higher velocity flow on the right side, which is outside of the blob, and there's a lower velocity flow going through the skin on the inside of the blob. And that creates these forces on these little skin blobs that are being pulled, in a sense, pulled apart, but they're also being pulled forward. And this basically creates a force from the viscous force on this little section of skin in the front of the blob. So that concludes the inspiration behind why these viscous terms exist. The next discussion will be of the viscous stress tensor.